Alright, so here we come to this instrument called the barometer. A barometer actually consists of a thick wall glass tube, and this thick wall glass tube is upside down, that means it's inverted, and is placed into like a trough of mercury, right? And over at the sides, we have atmospheric pressure acting down here. Now take note, when you invert it, there must be no gas inside here, alright? So there must be no air or gas inside here at all. Okay, so once you invert it, what happens is, because there's no air molecules at all, that means that air pressure inside will be equals to 0. Alright, so what happens is, when you place it inverted, atmospheric pressure, which is greater, start to force air downwards, and this air in turn push on the mercury, and the mercury, which has nowhere else to go, will actually enter the thick wall glass tube. Okay, and how high will this mercury column reach up to? Well, reach up to a point where the pressure over here underneath will be the same as the pressure due to atmospheric pressure at these two sides. Alright, so you can think of it as a seesaw with 3 players. First one, atmospheric pressure. Second one, atmospheric pressure. And third one, the mercury. Right, and this mercury column actually causes a pressure that is as great as atmospheric pressure. Because the pressure exists on this point is now the same as atmospheric pressure, the liquid column will no longer go up the thick wall glass tube. Now there are some rules to follow. So these are rules that you must know by heart. So number 1, at equilibrium. Okay, so this is probably the third time you have seen the word equilibrium. And what it really means is that there's no pressure difference, okay, within the external environment and the internal barometer. Okay, so at equilibrium, any horizontal line, but this horizontal line must be along or below the lowest liquid surface. Now this horizontal line that you draw will represent all the points with the same pressure. So example is this. Now first you must locate the lowest liquid surface. So here you have 1 liquid surface and 2 liquid surface. Which one is lower? Of course it will be this and this, right? So this rule only applies for horizontal lines that are along the lower surface or below. If you draw above, this rule will not work. Okay, take note, it must be lower or along the lower surface. Okay, what this means is that when I draw a horizontal line along the liquid surface, for example, what it means is that any point along this line, for example here, or even at A, at B, or C, they will be points with the same pressure. Okay, this pressure can be due to different things though. Like in this case, outside it is only due to atmospheric pressure at A and at C, but at B is entirely due to the mercury column. But it does not matter, because at any points on this line, any points, the pressure will be the same. Take note that this does not apply to areas outside these parts. Okay, so it does not apply to these parts and this part. Alright, now if we go even lower, and again we do the same thing, we draw a horizontal line that stretches across. Again, this line, because it's already below the lowest liquid surface, so any points along these lines will also experience the same pressure. Now check whether it's true. So here I've selected 3 points. Now for these 3 points, let's look at this. This will be affected by atmospheric pressure as well as the mercury pressure just above it. Same for this point. And this point over here will be affected by the mercury column that's above it. But this part of the mercury column, this part, is equivalent to my atmospheric pressure, right? So this height of the liquid column causes pressure that is equivalent to the atmospheric pressure. And after that, it still has an additional vertical height of mercury column that causes pressure on this point. So you realize that it is true that any point along these lines will experience the same pressure. Now, of course, the pressure will increase as the height of mercury above increase, right? And this pressure can be found using P equals to H rho G. Right, here I would like to add on. Now, question for you. What happens if the atmospheric pressure outside decreases? For example, as you go higher and higher above sea level and the atmospheric pressure decreases, what do you think will happen to the mercury column within a thick wall glass tube? Well, because here is pushing down less, right, compared to before, therefore by intuition, less mercury will go up this column, right? And so because of that, the column should actually drop in terms of its height. Another way to think about it is this, where if you draw a horizontal line over here, And this horizontal line represents points with all the same pressure. So the pressure here must be the same as here and must be the same as here. Now, if the pressure outside here decreases, what happens is that the pressure experienced by this point will also have to decrease. And the only way for it to decrease is when you have a decrease in the height of mercury column above. Alright? So let's go to example 1. Now, example 1 is when a barometer is placed at sea level. Okay, and what is the height of the mercury column in the barometer? Okay, and we are given density of mercury. I know it's not in your notes, but please take this down. It is 13593 kg per meter cube. Now, this is a very precise... Now, we're using the exact density of mercury so that we can find the most accurate height of mercury column later. Okay, so for gravitational field strength, we will also not be using the approximate value of 10. We will be using the more accurate value of 9.81 newtons per kg. Alright, and let's use rule 1. So pressure at B due to mercury column only is equals to pressure at A, which is due to atmospheric pressure only. Right, and this pressure at A is also the same as pressure at C, which is also due to atmospheric pressure only. Now, what is A, B, C? Quick recap. So A, B, C are here. A and C, they are due to atmospheric pressure only. B is due to the mercury column. Okay, and because they are along the same line, they have the same pressure. Right, so you can write this statement. PB, which is the same as PA and PC, it is equals to PATM, which is atmospheric pressure for in short. Okay, now PB, because it's just below mercury column and nothing else, so the pressure caused is actually only due to mercury column, and mercury is a liquid, so I can apply the pressure for fluids, which is H rho G, and H rho G will be the same as my atmospheric pressure. Right, and then you manipulate, you divide your atmospheric pressure by rho, which is 13593 for mercury, and you divide by 9.81, which is the value for G, and you'll find that you have 0.759. Here I've left out the units. What do you think the unit should be? Well, all along we have been using the SI units, pascals, kg per meter cube, newton per kg, so the final answer we get must be in SI units as well. So SI unit for height or length in general will be meters. Okay, so you round up to 2SF is 0.76 meters, and this is equivalent to 76 cm. So in fact, actually 1 atm, that means the atmospheric pressure, is equal to 76 cm of mercury column above. Okay, and this is written this way, 76 cm Hg. Now Hg is actually the chemical symbol for mercury. Okay, but how do we read this statement? Here, 76 cm Hg. So it is read as pressure due to 76 cm of mercury vertically above that point. Okay, so you must be able to break down this into this understanding. Alright. Now for example 2, the following barometers are placed together in a room at a certain altitude. So all of them are at the same altitude, which means they experience the same atmospheric pressure. Right? So because they are the same altitude, they have the same atmospheric pressure. Okay? And only the first barometer's mercury column is shown. What is the pressure shown on the first barometer? And express your answer in pascals. Okay, so for A, how do we do it? Well, let's put it in terms of mercury height once again. So this is 67 cm. Okay, so if I draw a horizontal line here, I know that atmospheric pressure over here and over here will be the same as this point over here. Right? And so my PATM, atmospheric pressure, will simply be the same as the pressure caused by this column of mercury above this point. And that is actually 67 cm of mercury vertically above. So I can write it as 67 cm Hg. Now, how do we convert 67 cm Hg into pascals? So you must really understand what 67 cm of Hg. Right, so this is read as pressure due to 67 cm of mercury vertically above. So what we can say is this. Therefore, pressure of ATM equals to H rho G. Here we know the height. It is 67 cm. Right, and let's use SI units because pascals is in SI unit. So the height will be 0.67 meters. Density of mercury is given by 13593. And of course, your gravitational field strength will take it to be 10. Alright, and you do your calculation. Okay, you realize it's 91,073 pascals. We change it to 3SF, it will be 91,100 pascals. Alright, so question is this above sea level or is this altitude below sea level? Well, this is definitely less than 1 atm, which is the atmospheric pressure at sea level, right? So it's lesser. That means there's less air column above. So I have gone up higher and therefore now there's less air column above. So this is of course a higher altitude than sea level. Okay, now how do we do part B? We draw and label the mercury levels in the following barometers, where you just follow the rule. A horizontal line drawn across will represent points of the same pressure. So if you consider the points here, now these points, they experience a pressure caused by the mercury alone, right? Now is it caused by the slanted height or is it caused by the vertical height of mercury? What have we learned? Pressure equals to H rho G. Does the H represent slanted height or vertical height? Well, it represents vertical height. Therefore, we are interested in only the vertical height of mercury on top of this point. And this vertical height must be the same as in the first case. Alright, so the mercury will have to reach up to this level in this particular barometer. Alright, and the same goes for the last barometer. You must have the same vertical height of mercury column above this point. But in this case, you realize this vertical height is even beyond our barometer. So what happens is the mercury will fill the barometer completely, and that is the maximum mercury that we can have. In this case, it will just be here, right? So this is the key idea. It is not the slanted height that we are interested in, but it is the vertical height that we are interested in. So same for this, it's not the slanted height that we are interested in, but the vertical height. Alright? Right, here we come to the first example of a manometer. Right, so a manometer has one side connected, X, connected to the gas supply, and another side Y that is open to the atmosphere. Now recall this, if I have both sides that are open to the atmosphere, right? So this side is going to be atmospheric pressure, and also this side is going to be atmospheric pressure. Then what will happen to the liquid column? Well, they will be at the same vertical height. Because imagine two people of the same force trying to press down on the same liquid in a manometer. Now, because they exert the same force, of course, the liquid level will stay at the same height, right? They'll be of the same height. However, in this case, we have X over here being connected to a gas tap. And what they don't show you here is that actually this gas tap is sealed off. Okay, that means whatever gas they pump in from this gas tap will be stuck inside here. So there'll be no escape of gas, and therefore it can create a pressure. Okay, so this gas tap has a pressure over here, whereas this part is just open to atmospheric pressure. So is atmospheric pressure greater or is the gas pressure greater? Well, what happens if you increase the pressure here? Well, if this guy exerts a greater force over here, of course this guy over here will move down and this one will move up, right? So same thing, if this has already gone down and this has already gone up, then of course our gas pressure is greater, right? And our atmospheric pressure is lower. Okay, so now let's consider what are the pressures acting at the points. To solve this, let us draw our favorite horizontal line. And this horizontal line we can draw along the liquid surface, right? But it's not just any liquid surface. So here I have two liquid surface, 1 and 2. Which one can I draw the horizontal line along? So it must be the lower one. Now once I draw this horizontal line, I know that these 2 points will definitely have the same pressure. So at this point over here, what exactly is causing the pressure? Well, it is only the gas pressure. So here, the only reason why I experience a pressure is because of the gas pressure. However, over here, what do you think is causing the pressure at this point? Well, there are 2 things, right? So number 1 is your atmospheric pressure because it's open to the air. And the second one is actually due to this mercury column, right? So this can be found by the P of mercury, which can be found using our H rho G later. Alright, so if we set up equation, the pressure at this point, let's say A, and the pressure at this point, let's say B, will be the same. So let's set up the equation. PA equals to PB. That means pressure at A equals to pressure at B. Pressure at A is only due to gas. So pressure of gas is at A. Pressure of B is due to atmospheric pressure at that particular altitude, plus the pressure due to mercury. Right? And why do we say that a manometer is used to find the difference in pressures? So watch this. The pressure of gas minus the atmospheric pressure will give me the pressure of mercury, which is easily substituted by H rho G, because that's how we're going to find the pressure due to that mercury anyway. Right? So what is the length H actually used to measure? Well, if we get the length H, we can find out H rho G. Okay, and this H rho G that we calculate is going to be due to the pressure of mercury alone, which is also equivalent to the difference in the pressure of gas and atmospheric pressure. So H rho G actually measures the difference between the gas pressure and the atmospheric pressure, and therefore our answer is D. So for example 2, they ask us what is the pressure exerted by the trapped air, and we have to express our answer in SI units. Okay, so first of all, we analyze the diagram and we realize that there's a gas supply over here on this side, and there's trapped air on this side, and in between them is our mercury that is stuck, right? So again, which side has the higher pressure? Well, this side is lower, so definitely the gas pressure here is exerting a higher pressure. But again, if we draw our favorite horizontal line, then we know two things. Then we know that the pressure at this point, let's call it A, will be equals to the pressure at this point, let's call it B. So always set up your equation first. PA equals to PB, right? And what is PA, the pressure at A, due to? Well, it's due to the trapped air, and it's also due to the mercury column above. So for trapped air, I'll write this pressure of trapped air in short, plus the pressure of the mercury column, which is simply 12 cm worth of mercury above it, will be equals to the pressure due to the gas supply at B. And this pressure due to the gas supply is 150 cmHg. Right now, you must be comfortable in dealing with cmHg, and you can in fact simplify it before you convert it to SI units. So if they want the pressure of trapped air, it would just be PTA equals to 150 cm of mercury minus 12 cm of mercury, which will give me 138 cm of mercury. Okay, and here we want to convert 138 cm of mercury into pascals. So again, we ask ourselves, what does 138 cm of mercury means? Well, it means the pressure that is equivalent to having 138 cm of mercury above you or above that point. So let's use our H rho G. So PTA equals to H rho G. H will just be 138 cm, but I want it in SI units, so I must convert everything into SI units first. Rho is 13600, and finally G is 10. Okay, and answer will be 187680 pascals. If you change it to 3SF, it should give you 188 kilopascals. Now, many of you might ask, why am I using kilo? Is kilopascals still the SI units? Well, it is, because it's pascals. I'm just adding a prefix in front of it, and that is still the SI units. Okay, just like standard form, you can also change it to 1.87 times 10 to the power of 5 pascals. And if you recall, 1 atmospheric pressure is defined as 101.325 pascals, which is also presented to you as 1.01 times 10 to the power of 5 pascals. So all these are still in SI units as long as it's in terms of pascals. Right, in example 3, we have a manometer that is connected to an air pump as shown. Now, manometer is filled with water, which has density 1000 kg per meter cube. Atmospheric pressure is 100,000 pascals, and they want the air pressure P caused by the air pump. So let's take a look at this manometer. So again, we draw our favorite horizontal line that is along the lowest liquid surface, right? And here we have 2 points. Let's call this A, and let's call this B. And we know that the pressure at these 2 points must be the same. So pressure at A is purely due to the gas pressure, and pressure at B is due to the mercury column above. And is it due to anything else? Well, over here, if there were air molecules, then we have to account for that. But here we have a vacuum, that means there's no air molecules at all. So the pressure at B is purely due to the mercury column. So setting up our equation, we have this PA, which is equals to PB. And PA is purely due to the pressure P caused by the air pump, so I'll just write it as P. Okay, this is not mercury, it should be water. So PB is due to the pressure of water above, right? So, which can be found using H rho G. So I'll just convert it to H rho G. H will be 1 meter, rho will be 1000 kg per meter cube as given, and G will be 10. Alright? And the answer will be 10,000 pascals. Take note that in this case, we have not used the atmospheric pressure at all, so it really depends on the question. Sometimes you do not have to use it at all. Alright, now next question, question number 4. A manometer which contains unknown liquid X and mercury is shown in the diagram below. Now determine the density of unknown liquid X, given that the density of mercury is 13.6 kg per meter cube. Okay, here we have a mistake. It is not 13.6 kg per meter cube. It is 13600 kg per meter cube. So take note of this. So over here, again, we have this time two liquid surface. This time we have two liquids involved, so it seems a bit more complex. So we have three liquid surfaces, 1, 2, and 3. Again, we can only choose the lowest liquid surface, right? And usually we treat this as like our gauge. So what it does is that it is squashed in between two other pressures, whether caused by gas and liquid or whether just caused by gas. And this pressure will be trying to tilt our liquid level accordingly, right? So the gauge liquid that we have, so in this case, it is our mercury, and we draw our horizontal line. So again, this point over here I'll call it A, and this point over here I'll call it B. So no matter what, pressure at A equals to pressure at B. Okay, what exactly is causing the pressure at A? Well, of course, there's the atmospheric pressure, so that I'll write as my PATM. And there's also this 60 mm of mercury, right? So I have to add in my 60 mm mercury, and this will be equal to the pressure at B. Now, pressure at B also has atmospheric pressure, and it also has a liquid column that contributes to the pressure, right? So this liquid column is going to be my 105 mm of liquid X. Okay, now both sides have atmospheric pressure. So atmospheric pressure is the same. So I'm going to cancel this out and this out. So straight away, we have 60 mm of mercury being equals to 105 mm of liquid X. So let's break this down using our H rho G. So 60 mm of mercury in terms of H rho G will simply be 60 over 1000 meters multiplied by density of mercury, which is 13600, multiplied by G, which is 10, right? And it's equivalent to the pressure created by 105 mm of liquid X. So here 105, we change it to meters, and the rho we don't know, and finally we add the 10 in. Okay, again 10 and 10 will cancel, and so we can find our rho. Our rho will just be 60 over 1000 multiplied by 13600 divided by 105 over 1000. Okay, work through this. You'll find the density to be 7,771 kg per meter cube in SI units, right? Because all throughout I'll be using SI units. So final answer, I know it has to be in SI units. Now convert this to 3SF is 7770 kg per meter cube. And this is our answer. Alright, by this case, the answers given here are all in 2SF. So of course the answer will be A. Now next question 5, we have some trapped air in a mercury barometer as shown below. So once you have trapped air, this is not a vacuum because there's something there. Alright, so how do we use a barometer to help us solve this question? Well, first there's atmospheric pressure acting at the sides, and this atmospheric pressure causes the mercury column here to rise, right? But same thing, draw a horizontal line. So you can choose any 2 points. So I'll choose here, here, and here, just so you know. So let me call this A, let me call this B, and let me call this C. Right? So you will know that the pressure at A is the same as the pressure at B, which is the same as the pressure at C. Okay? Now, pressure at A and pressure at C are purely due to atmospheric pressure itself. Okay, so let me just choose randomly PB equals to PC to work on. So PB equals to PC, pressure at C. Now, PB is caused by the mercury column as well as the trapped air. So I can split this up into P, pressure of trapped air, plus the pressure of the mercury column, right? In this case, it is 83 minus 9 in terms of its height. So it's 74 cm of mercury. And PC, of course, is purely atmospheric pressure, which is given over here to be 76 cm of mercury. Now, they ask us what is the pressure exerted by the trapped air. Well, this is a one-step question now. Pressure of trapped air will simply be 76 cm of mercury minus 74 cm of mercury, which will give us 2 cm of mercury. Now again, this is units of pressure, so I do not have to change it to SI units unless they ask me to do so. So in this case, they did not, and answer is A. Alright, now I want you to try questions 6 and 7 yourself, and these are the harder questions, but I trust that you should be able to do it. Thank you.